So ultimately, respiration is about gases. In this section, we'll be examining how gases, specifically oxygen and carbon dioxide, are delivered from the lungs into the blood and to the tissues, as well as how carbon dioxide is removed. Before we go there, we really need to understand the composition of air and how these gases behave when they contact water. So the air we breathe is 78.6% nitrogen, 20.9% oxygen, and 0.04% carbon dioxide. 0 to 4% of it is water vapor, depending on where you live, the temperature, the humidity. Then there are some minor gases like argon, neon, helium, methane, and ozone. We don't really concern ourselves with those. We need to understand Dalton's law. Dalton's law states that the total atmospheric pressure is the sum of the contributions of each of the individual gases. Each individual gas has a partial pressure to the whole atmospheric pressure, a separate contribution. Remember that we've said at sea level, the pressure is 760 millimeters of mercury, and that's what we define as 1 atmosphere. So the partial pressure here, when we look at nitrogen, is 78.6%. So 78.6% of that 760 millimeters of mercury is due to nitrogen. And so that is 597 millimeters of mercury. The partial pressure of oxygen at sea level, if there's 20.9% oxygen in the air, we take 20.9% of 760 and we come up with 159 millimeters of mercury. Then we look at water. If we've got about 0.5% in there, blah, 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 we have 3.7 millimeters of mercury. The other important one here is partial pressure of carbon dioxide. At about 0.04%, we end up with 0.3 millimeters of mercury. And if we total all of these partial pressures, then we end up with the atmospheric pressure at sea level, which is 760 millimeters of mercury. Now, the composition of the air we actually inspire and the air that's in the alveoli is different because of 3 influences. First, as air enters the respiratory tract, it's humidified when it contacts the mucous membranes. So the alveolar partial pressure of water is more than 10 times higher than it is in the inhaled air. Also, the freshly inspired air mixes with residual air that's left from a previous respiratory cycle. Thus, the concentration of oxygen is diluted and is enriched with carbon dioxide that's on its way out of the system. The third factor that changes the composition of the alveolar air is that it exchanges oxygen and CO2 with the blood. So the PO2, or the partial pressure of oxygen in the alveolar air, is about 65% of that of inspired air because some oxygen is jumping out of the air into the blood. And then the partial pressure of carbon dioxide, or the PCO2, is more than 130 times higher. This table below summarizes these differences, and they have a big impact on how and why oxygen and carbon dioxide move onto the blood. So gas exchange occurs in the alveoli. We call this alveolar gas exchange. It's the back and forth traffic of oxygen and carbon dioxide across the respiratory membrane. The air that's in the alveolus is in contact with a film of water that covers the alveolar epithelium. In order for oxygen to get into the blood, it has to first dissolve in water. Then it can pass through the respiratory membrane, which separates the air from the bloodstream. And for carbon dioxide to leave, it has to pass the other way. It has to diffuse out of the water film in the alveolar air. So basically there's 2 steps. We have to dissolve it in water and then cross the membrane. And this water step will really influence how gases exchange. Again, gases will diffuse down their own concentration gradient until the partial pressure of each gas in the air is equal to its partial pressure in water. If a gas has a greater partial pressure in water than it does in air, then it diffuses into the air. The smell of chlorine near a swimming pool is evidence of this. If its partial pressure is greater in the air, then it will diffuse into the water. Spend a moment thinking about this. It's important for our understanding of the next section. So Henry's law states just this. At the air and water interface, for a given temperature, the amount of gas that dissolves in the water is determined by its solubility in water and its partial pressure in the air. So we're combining two components now. We just spent a little time thinking about this partial pressure in the air and whether a substance will move down its concentration gradient into the water. But now we have an added portion, the solubility. So the greater the partial pressure of oxygen in the alveolar air, the more oxygen the blood is going to pick up. That makes sense, yeah? Since blood arriving at the alveolars has a higher partial pressure of CO2 than air, it releases CO2 into the air. Make sense? So in these figures on the right, we'll look at the top one. The partial pressure of oxygen in the alveolar air is initially higher than the partial pressure of oxygen in the blood. Thus, oxygen diffuses into the blood until the two are in equilibrium. In the case of carbon dioxide, the partial pressure of carbon dioxide in the arriving blood is initially higher than the partial pressure of carbon dioxide in the air. Carbon dioxide thus diffuses into the alveolus until the two are in equilibrium. It only takes about a quarter of a second for both gases to reach equilibrium, so this happens pretty quickly. So the language about this movement of carbon dioxide and oxygen is called loading and unloading. At the alveolus, the blood is said to unload carbon dioxide and load oxygen. So we're unloading CO2 from the blood and loading O2 onto the blood. All of this loading and unloading involves the red blood cells or erythrocytes. And the efficiency of it depends on how long the red blood cells stay in the alveolar capillaries. As I just mentioned, it takes only 1/4 of a second for equilibrium to be reached. At rest, the red blood cell spends on average about 3/4 of a second in the alveolar capillaries. During strenuous exercise, about 0.3 seconds, and that's still enough time for the 0.25 seconds that are necessary for the alveolar exchange. Now, it's important to remember that each gas in the mixture is going to behave independently of the other gases in that mixture. That means one gas does not influence the diffusion of another gas. There are some factors that are going to affect the gas exchange naturally. The pressure gradient of the gases we've really already examined. But let's look at the real numbers. The partial pressure of oxygen in the alveolar air is about 104 millimeters of mercury. In the blood, we see the partial pressure of oxygen being about 40 millimeters of mercury in the lungs. Thus, we can see that there's a higher gradient moving from the alveolar air into the blood. For CO2, we see that in the blood arriving at the lungs, it's about 46 millimeters of mercury and about 40 millimeters of mercury in the alveolar air. So which way is the carbon dioxide naturally going to move? At high altitudes, the partial pressures of all the gases are actually lower, so the gradient difference is less. It's not that there's less oxygen in the air up here. It's mainly that this gradient difference is less. So less partial pressure of oxygen means that less oxygen is diffusing into the blood for each breath of air we take. In hyperbaric oxygen therapy, we treat people with oxygen that is under greater than 1 atmosphere of pressure. So a higher pressure, as if we were below sea level slightly. The gradient difference at this point is greater, and thus more oxygen diffuses into the blood. We use this technology to treat gangrene and carbon monoxide poisoning. We'll discuss carbon monoxide shortly, but it has a higher affinity for the red blood cells, so we have to essentially give oxygen a bigger push so that it can compete with the carbon monoxide and drop it off the red blood cells. The other big factor that affects gas exchange is the solubility of each of those gases. Now, carbon dioxide is 20 times more soluble than oxygen. So equal amounts of oxygen and CO2 are exchanged across the respiratory membrane because CO2 is so much more soluble, it diffuses more rapidly. So even though the pressure gradient of O2 is much greater, its solubility is less. And so that makes the exchange right about equal. Now, oxygen is about twice as soluble as nitrogen, so it has a little bit of an advantage that makes up for its lower partial pressure in crossing the respiratory membranes. Membrane thickness will naturally affect gas exchange. They're only about half a micrometer thick, which presents little obstacle to diffusion at all. However, in the instance of pulmonary edema, there is left side ventricular failure in the heart, which means it's not pushing enough blood out into the system, which means we have a backup of blood in the pulmonary circuit. This causes thickening of the respiratory membranes and thus less efficient gas exchange. Pneumonia also causes thickening of respiratory membranes. There's less efficient gas exchange because the gases have much farther to travel between the blood and the air, and they cannot equilibrate fast enough to keep up with the blood flow. That 0.25 seconds, it takes a lot longer to go across a thicker membrane. Also, the membrane surface area. 100 milliliters of blood in the alveolar capillaries gets spread thinly over the size of a tennis court, 70 meters squared. In emphysema and lung cancer and tuberculosis, the surface area for gas exchange is highly reduced. It's also very reduced in smokers' lungs. The final factor that could affect gas exchange is the ventilation-perfusion coupling. That is the ability to match the ventilation, the airflow across the alveolar surfaces, to the perfusion or the blood flow across the alveolar surfaces. Gas exchange requires both good ventilation of alveolus and good perfusion of the capillaries. Usually, the ventilation-perfusion ratio is about 0.8. A flow of 4.2 liters of air and 5.5 liters of blood per minute at rest. This figure is going to be a great figure for our reference. It summarizes the changes in the partial pressure of oxygen and the partial pressure of carbon dioxide along all the circulatory routes. So far, we've just dealt with alveolar gas exchange. Next, we'll deal with gas transport in the blood, and then we'll deal with the systemic gas exchange. How do we drop off and pick up these gases at the tissues? This graph shows us the oxygen loading in relation to the partial pressure gradient. The rate of loading is going to depend on the steepness of the gradient from the alveolar air to the venous blood. Here we're seeing air at sea level, and we see a steeper gradient of O2 diffusion into the blood. This is an example of high altitude. The gradient is less from the atmospheric air to the venous air. And then here we're looking at the hyperbaric chamber, where we've increased the atmospheric pressure, gives a much steeper gradient and much more rapid diffusion of oxygen. Here you can see the difference between the alveoli in health and in disease. The normal alveolar walls look like something like this in a microscope. However, during pneumonia, we'll see that there's edema in the lungs and the alveolar walls have thickened, and so gas exchange is much less efficient. In emphysema, the alveolar membranes have begun to break down, and the neighboring alveoli join to form larger but fewer alveoli. This decreases the surface area for gas exchange. And these final two figures show us about ventilation-perfusion coupling. The negative feedback loops will adjust airflow and blood flow to meet each other. Basically, this says that as we see decreased airflow, then we see reduced oxygen in the blood vessels and vasoconstriction of the vessels, and thus decreased blood flow. Once the increased airflow happens, we'll see elevated partial pressure of oxygen in the blood vessels. Thus, we see vasodilation of the pulmonary vessels and increased blood flow. So basically, it's showing that blood flow will match the airflow. In this figure, we're showing that airflow will match blood flow in a very similar way. So the two, ventilation and perfusion, are continually adjusting to meet each other and have the ideal rate of gas exchange. So wow, that is a lot of information to absorb, but it really is amazing that these, just because of the various partial pressures of the gases in our atmosphere, that it just works. I mean, think about it. This is why I find physiology absolutely fascinating. But you know what it's time for now? It's time for some diagramming. I recommend that you focus on the beginning part of this diagram, the concentration gradients of gases. Really figure out for yourself why it is that air is moving across the respiratory membranes. And what's going in which direction? Well, that part's kind of obvious. But why is it going in that direction? Based on these partial pressures. Think about hyperbaric oxygen chamber. And also think about our situation here at high altitude. Why is it more difficult for us to breathe up here? Now, of course, we live here. We make some adaptations that make it much easier for us. But when people visit, they have a rough time. And remember, it's not because there's less oxygen in the air. There's still 20.93%, whether you're at sea level or at high altitude. It's just that the driving force behind it is less. Get this stuff straight, and then I'll see you for the section on gas transport and systemic gas exchange.